Good morning, everyone. Today, I'll be discussing data collection techniques, image analysis, and visual interpretation. This topic is fundamental in geospatial studies, land governance, and remote sensing application. My name is Dr. Upasana Soduri, and I am a research scholar at the Center of Excellence on Land Governance, Assam. Through this presentation, I aim to provide insights into various methods of data collection, the role of image analysis in spatial studies, and the importance of visual interpretation in extracting meaningful information from geospatial datasets. The discussion will cover key concepts, methodologies, and practical application relevant to land governance and geospatial research. I look forward to engaging you all on this critical subject. Moving on, the various technologies used in remote sensing for Earth observations are highlighted. So, remote sensing relies on a diverse range of tools, including satellites and airborne technologies, which continue to evolve. This includes our older satellites, newer high resolution satellites like the Sentinel series, as well as airborne laser sensors and drones. One of the key challenges in remote sensing is handling the vast amount of data collected over time. To address this, advanced IT systems such as cloud computing and machine learning techniques are utilized. These technologies help process and analyze large data sets efficiently, converting raw remote sensing data into actionable insights. Ultimately, the integration of all these modern technologies enhances decision making processes in various applications, including environmental monitoring, disaster management, as well as land governance. So, moving on, the introducing the basic concept of remote sensing by breaking it into two key concepts, that is remote and sensing. So the term remote refers to something that is not in direct physical contact. In the context of remote sensing, this means observing and gathering information from a distance without physically interacting with the object or area being studied. So similarly, sensing refers to the process of collecting data or information, whether it is temperature, pressure, images, or any other environmental parameters. When combined, remote sensing refers to the technique of obtaining information about the Earth's surface or atmosphere using sensors placed on satellites, aircrafts, or drones, allowing us to analyze and monitor changes over time without any physical contact. Moving on to the next slide, the concept of natural remote sensing, which is something we experience in our daily lives. So, as we can see, a beautiful landscape on the left, a scene filled with trees, flowers, waters, and people. This represents our real world environment. In the middle, we have an eye which symbolizes the sensing or the perceiving processes. Our eyes act as natural sensor, capturing the visual information from the surrounding. On the right, we see a human brain. On the eyes, once the eyes capture the image, the brain processes and analyzes the information, which allows us to interpret what we see, whether it's identifying colors, recognizing objects, or understanding the scene. Finally, the processed information becomes knowledge. This is similar to how artificial remote sensing works, where the sensors like the satellites or drone capture data which is then processed and analyzed to generate meaningful informations. Moving on. So, artificial remote sensing, which is how technology mimics natural perceptions to gather information about the Earth from a distance. So, the process begins with a satellite which acts as the sensor capturing data from the Earth's surface. This is the sensing or the perceiving phase. The data is then transmitted to the ground station with large antennas where it undergoes analysis. Next, the extracted information is processed using computers, which generate meaningful outputs. On the bottom right, we see two examples of such outputs, a raw satellite image and a classified image, where different land cover types are highlighted in different colors. This structured approach allows us to monitor environmental changes, urban growth, disasters, and much more, making remote sensing a crucial tool for decision making in various fields. Moving on, here is an overview of how satellite sensors function in remote sensing. It explains how satellite captures data using specialized sensors that detect electromagnetic radiation from the Earth's surface. These sensors are essential for environmental monitoring, land use mapping, climate studies, and disaster management. So, by one, I'll explain satellite sensors and their functioning. So, satellites are equipped with advanced imaging sensors, specifically multispectral or hyperspectral sensors. These sensors are designed to detect and measure electromagnetic radiation, that is light, that is either reflected or emitted from the Earth's surface. The data is then used to analyze various aspects of the Earth's environment, such as land cover, vegetation health, and temperature variation. Moving on to the electromagnetic spectrums and bands. So the electromagnetic spectrum is the range of all type of electromagnetic radiation classified based on their wavelengths. So electromagnetic spectrum is the Earth's surface interacts is the how the Earth's surface interacts with the sunlight in two major ways. First of all, reflection. Sunlight hits the Earth's surface and bounces back into space in different wavelengths. Secondly, emission. The Earth also absorbs solar energy and later emits it as infrared or thermal radiation. Satellite sensor then detects this radiation and record it as images for analysis. Then we have spectral bands. So electromagnetic spectrum is divided into different bands, each corresponding to a specific range of wavelengths. Some key bands in remote sensing includes visible light, that is blue, green, red, which is used for natural color imaging. Then we have infrared NIR in short, which helps in vegetation analysis. Then we have shortwave infrared or SWIR, which detects moisture content in soil and vegetation. Then we have thermal infrared TIR, which measures surface temperature and heat emission. And also we have microwave and radio waves used in radar and passive remote sensing applications. So the importance of electromagnetic spectrum in remote sensing is different objects on Earth interact uniquely with electromagnetic radiation. By capturing and analyzing different spectral bands, we can extract valuable information about the vegetation health monitoring. So NIR, that is near infrared, helps identify stressed or healthy plants. Similarly, water body analysis can also be done using infrared bands, which helps us in distinguish water and land. Also, critical mapping such as urban and land use mapping can also be done by studying different materials such as concrete, soil, vegetation, as they have distinct spectral signatures. Moving on, we also use this in disaster monitoring. So, thermal infrared helps detect wildfires, and radar imaging is also useful for flood mapping. So, this highlights the fundamental principle behind satellite remote sensing, which captures electromagnetic radiation in different spectral band, and by using specialized sensor, satellites can provide valuable data that provides environmental monitoring and monitoring sources, remote sensing management, and scientific research. So, understanding the electromagnetic spectrum is essential for interpreting satellite images and extracting meaningful insights for various applications. Moving on, this explains how satellite sensor works and their classification into passive and active sensor. So, first of all, we have optical sensor. Satellites use sensors that detect electromagnetic spectrum, but there are two types of sensors. First is passive sensors, for example, infrared camera, which rely on sunlight to detect reflected energy. And then we have active sensor, for example, radar or lidar, which emits their own energy and measure the reflection. Then we have filters and detectors equipped in the sensors. So sensors use filters to split incoming light into different wavelengths or wavelength bands, which are detected separately for detailed analysis. Then the digital data capture. As satellite orbits the Earth, they continuously collect data from each spectral band, storing it as digital numbers that represent radiation intensity. Lastly, composite image formation. So, the collected data from multiple bands is combined into true color or false color images to highlight specific Earth features such as vegetation, water bodies, or other important areas. So, this illustration highlights the difference between the passive remote sensing, which uses sunlight, and the active remote sensing, which uses emitted energy like radar or lidar. Moving on. Here we'll explain the difference between true color composite and false color composite in satellite imagery. So the true color composite, that is TCC, uses the visible spectrum, that is the red, green, blue, and which is also called as RBG, to create images that resembles what the human eye naturally sees. So vegetation appears green, water bodies as blue, and urban areas as gray or white. Similarly, then on the opposite, we have false color composite, that is FCC, which uses non-visible spectral bands or rearranges visible bands to enhance specific features. For example, healthy vegetation appears bright red instead of green, making it easier to analyze land cover. Similarly, water bodies appear dark blue or black, and urban areas may appear in shades of blue or gray. So FCC is particularly useful in applications like vegetation, health monitoring, land use application, and water analysis. Moving on, this slide explains pixels. So, which are the smallest building blocks of digital images? So, the term pixel stands for picture element, and each pixel is a tiny dot that forms part of an image on a display screen or printed sheet. Just like a bit is the smallest unit of digital information in a computer, a pixel is the smallest unit that is a display or printer can manipulate to create letters, numbers, and graphics. So the image illustrates how an image, whether a text or a photo, is composed of numerous pixels arranged in a grid. So the higher pixel density results in better image clarity and resolution. Moving on, here's an overview of the spectral bands used in Landsat sensors, specifically Landsat multispectral sensor and Landsat TM and ETM in 1982. So, Landsat MSS, that is multispectral sensor, captures data in 4 spectral bands, that is red, green, and 2 NIR bands. Each band has a spatial resolution of 79 meters. Then we have Landsat TM, that is thematic mapper, and ETM, enhanced thematic mapper plus. So this includes 8 spectral bands covering visible, near infrared, MIR, mid infrared, and thermal infrared regions. Notable improvements include higher spatial resolution, that is 30 meters in most bands. Then we have panchromatic band, that is increased to 15-meter resolution in enhanced thematic mapper plus for better image clarity. And then we have thermal infrared band, that is 120 resolution for temperature analysis. So these sensors are crucial for land cover mapping. Then what is the what is image resolution? So the concept of image resolution refers to the number of pixels in an unit area of a digital image. Higher resolution means more pixels, leading to sharper and more detailed images, while lower resolution results in pixelization or loss of clarity. So the term resolution is commonly used in both traditional and digital photography to describe the quality of an image. The image at the bottom illustrates this concept, showing how increasing pixel reduces decreasing pixelization reduces clarity. In remote sensing, higher resolution is crucial for detailed analysis such as urban mapping, vegetation studies, and land use classification. Moving on, this introduces the four types of resolution in remote sensing. So we have mainly four types of resolution in remote sensing. First one is spatial resolution, then we have temporal resolution, spectral resolution, and lastly radiometric resolution. Spatial resolution refers to the size of the smallest object or that a sensor can detect, measured in meters or centimeters. So higher spatial resolution provides finer details. Then we have temporal resolution, which indicates how frequently a satellite captures images of the same location. It is crucial for monitoring dynamic changes like urban expansion or deforestation, etc. Then we have spectral resolution, which defines the ability of a sensor to distinguish between different wavelengths of light. Higher spectral resolution enables better material identification, such as vegetation health analysis. Radiometric resolution represents the sensitivity of a sensor in detecting slight differences in energy levels. Higher radiometric resolution improves the ability to distinguish subtle variation in reflectance. So this resolution collectively determine the quality and ability of the satellite imagery in various geospatial analysis. Moving on, a detailed explanation on spatial resolution in satellite imagery. So as we know, spatial resolution refers to the size of a pixel on the ground. So higher spatial resolution, that is 0.41 to 4 meters, means each pixels represents a smaller area, providing more detailed information of almost 4 meters. A lower resolution, spatial resolution can be range from 30 to 1000 meters, meaning each pixel covers a larger area, resulting in less detail. So the diagram shows how different pixel size 30 meter, 5 meter and 1 meter affects image clarity. Smaller pixel captures fine details, making features like house more distinguishable. Higher resolution is ideal for detailed land analysis, while lower resolution is useful for broader regional studies. So now this explains the temporal resolution in detail. So temporal resolution, which refers to how often a satellite capture images of the same location over time. So higher temporal resolution means more frequent observation, useful for monitoring changes. Then lower temporal resolution means less frequent imaging, which may not capture rapid changes effectively. So the image illustrates various satellite revisit time. One satellite revisits every 16 days, which is can be classified as less frequent observation. Another revisits every 11 days, that illustrates more frequent observations. So higher temporal resolution is crucial for dynamic environmental monitoring and tracking land use changes. Then we have spectral resolution, which refers to a sensor's ability to detect small differences in wavelength by capturing reflected radiation in different spectral bands. Higher spectral resolution means more bands allowing detailed material identification. Higher perspectral sensor capture hundreds of bands, for example 220 bands, which is ideal for precise vegetation, mineral or water quality studies. Then we have medium spectral resolution, which captures 3 to 15 bands, typically used in environmental monitoring. Then we have low spectral resolution, which has only 3 bands, and that is RGB, red, green, and blue, or panchromatic, providing basic imaging. So the is diagram shows different spectral resolution from panchromatic, that is black and white, to multispectral and hyperspectral imaging, highlighting the increasing detail in spectral data. Okay, then as you can see from these two slides, can you tell the color of the platform top? How about the sash? So, for example, this is panchromatic imaging. Then we have this in increasing spectral resolution adds more information. So, a colored image will give us more uh, information than a panchromatic, that is a black and white image. Moving on to the discussion of radiometric resolution. So, the radiometric resolution refers to a sensor's ability to detect small differences in radiation intensity for each pixel in an image. Higher bit depth means more levels of brightness can be recorded, improving the sensor's ability to distinguish fine details. The examples compares different bit depth. 1 bit means 2 levels of, that is black and white. 4 bit means 16 levels of gray, and 8 bit is equals to 256 levels of gray, that is smoother transition. So AVHRR sensor can capture 10 bit, that is 1024 levels per pixel, while Lancet captures 8 bit 256 levels, meaning AVHRR has finer radiometric detail. In short, higher radiometric resolution improves image quality by capturing more subtle variation in light intensity. Further, radiometric resolution can be explained by showing different bit depths affect the image quality. So the image represents the same picture at different radiometric resolution, that is bit depths. So 8 bit, that is 256 gray shade, provides the most detailed and smoothest image, while 4 bit, that is 16 gray shades, reduces detail, making the image less smooth. Then 2 bit, that is 4 gray shade, further loses detail, creating a blocky effect. And a 1 bit, that is 2 gray shades, black and white only, loses almost all details, showing only extreme contrast. So in summary, higher radiometric resolution captures more subtle variation in brightness, improving image quality and interpretation. Moving on, we can here is a comparison between different satellite based on different types of resolution. So, spatial resolution is how an image is. Okay, so Lancet, that is the Lancet TM, that is thematic mapper, that is 30 meter in resolution, spatial resolution, and Lancet multispectral sensor, that is 75 meter, provides higher spatial spatial resolution, more detail. Then GOES, AVHRR, and CWIVS is of 1 kilometer, having lower resolution, less detail. Then we have MODI's data offers multiple resolution in 1 kilometer, 500 meter and 250 meter. Then moving on to the spectral resolution. So the spectral resolution, as we already said, is the number of bands a satellite captures. So MODIS has a 36 band and Landsat thematic mapper has 6 band, have excellent spectral resolution. So on the other hand, GOES have 1 band and is considered as poor spectral resolution. Then we can compare this with temporal resolution. So how frequently temporal resolution is how frequently images are captured. So GOES captures data 15 minutes, has excellent temporal resolution with frequent updates, while Landsat data have poor temporal resolution, that is 2 weeks, that is infrequent updates. And on the last is MODI, C-Waves and AVHRR captures images daily but are rated fair to poor. Okay. So Landsat satellites are good for high. So from this comparison, we can understand that Landsat images satellites are good for high detail images but have low visit frequency. Then GOES is great for frequent weather monitoring but lacks detail. MODIS provides a balance of spectral and temporal resolution with moderate spatial detail. Now this slide explains electromagnetic radiation. So electromagnetic radiation, which is a form of energy that moves at the speed of light in a harmonic wave pattern. So the key points of electromagnetic radiation or EMR are, so nature of EMR consists of both electric and magnetic field that oscillate perpendicular to each other and to the direction of wave propagation. So source of EMR, it is emitted and absorbed by charged particles behaving as both a wave and a particle. So it has a dual nature. And the wave components is as from the diagram, it illustrates how the electric, that is E, and the magnetic M fields are orthogonal at right angle to each other as the wave moves forward. So EMR is essential for remote sensing as it interacts with surface differently based on its wavelength and frequency, allowing us to study Earth's features using satellite data. So this illustrates the nature of electromagnetic radiation and how it propagates through space. So the diagram shows how electromagnetic radiation consists of electric, that is shown in red, and the magnetic, that is shown in blue, fields which oscillate perpendicularly to each other and to the direction of wave propagation. Propagation direction. So the wave travels along the x-axis while the electric field oscillate along the z-axis and the magnetic field oscillate along the y-axis. And the rightmost diagram provides a cross-sectional view highlighting the perpendicular relationship between the electric and the magnetic field. So this visualization helps us understand how EMR moves through space, which is fundamental in remote sensing. Different wavelengths of EMR interact uniquely with Earth's feature, allowing us to capture detailed information. Then the properties of electromagnetic radiation. So the field of EMR consists of two perpendicular fields, as I already said, that is electric field and the magnetic field. And the wave theory of EMR, velocity, that is V or C, is the speed of light is 3 into 10 to the power 8 meter per second. Frequency F, the number of wave cycle per seconds, and wavelength is the distance between two successive wave crests. And the wave equation is the relationship between these properties is given by V equals to frequency by wavelength. V equals to frequency into wavelength, where velocity is equals to, that is frequency into wavelength. So the diagram shows how electric and magnetic field oscillate perpendicular while propagating through space, and the bottom diagram illustrates different wavelengths. Higher frequency means shorter wavelengths, while lower frequency corresponds to longer wavelengths. Understanding these properties is crucial as different wavelengths interact differently with Earth's features and atmosphere. The electromagnetic spectrum, which includes all possible frequencies of electromagnetic radiation. So, the electromagnetic spectrum represents the range of all electromagnetic waves, classified based on their wavelengths and frequencies. Classification of electric EM waves, electromagnetic waves. We can classify it in high energy waves, visible light, or low energy waves. Okay, so the high energy waves include the shorter wavelengths and higher frequency, that are gamma rays and x-rays, which are used in medical imaging and nuclear application. Then we have, in higher energy waves, we have ultraviolet rays, which is found in sunlight and used in sterilization. Then in the middle, we have the visible light, the only part of the spectrum that is visible to the human eye, which range from violet, shorter wavelength, to red, longer wavelength. Okay. Then we have the lower energy waves, that are we can say longer wavelength and lower frequencies. So this includes infrared rays, which is used in thermal imaging and remote sensing, radar, TV, short waves, radio waves, which are used in telecommunication or communication broadcasting. Okay, so lower energy, these are called lower energy waves. So energy and wavelength relationship can be explained as shorter wavelength have higher energy, for example gamma rays, X rays, UV rays. Then we have longer wavelength that have lower energy, that is radio waves, AM waves, FM. Okay, so understanding this is important. Okay, moving on. This explains the spectral bands in remote sensing, focusing on how different wavelengths of electromagnetic radiation are used for various imaging purposes. So, spectral bands and wavelength. The table categorizes different spectral bands, their wavelength ranges in micrometers, and their application in remote sensing. So, what it is uses in remote sensing. So, blue band, that ranges from 0.44 to 0.5 micrometers, is best for atmospheric and deep water imaging, as it penetrates up to 50 meters in clear water. Okay. Then we have the green band, which ranges from 0.5 micrometer to 0.57 micrometer, helps in vegetation and water structure imaging, reaching up to 30 meter in clear water. Then we have the red band, that ranges from 0.62 to 0.7 micrometer, useful for identifying man-made objects, vegetation, water bodies up to 9 meter deep. Next, we have near infrared, which ranges from 0.7 micrometer to 1.3 micrometer, ideal for vegetation health monitoring, as healthy plant reflects it very strongly. Then we have mid infrared, it ranges from 1.3 to 3.0 micrometer, used for detecting vegetation, soil moisture, and forest fires. Coming to the next is the thermal infrared, which ranges from 3 micrometer to 14 micrometer, measures emitted heat radiation for applications such as geological study, thermal currents, fire detection, and during night observations. Then we have microwave, that is from 1 mm to 1 meter, essential for terrain mapping and object detection even through clouds and during night time. So each spectral bands plays a crucial role and have different uses in applications like vegetation analysis, water body study, soil moisture assessment, fire detection, etc. Then this slide represents Lancet 8 imagery of its example of Lancet 8 imagery of Guwahati city. So Guwahati city, Assam, highlighting its capabilities and how it is used in land use classification. So Lancet 8, an overview of Lancet 8 is that Lancet 8 is also known as Lancet Data continuity mission was launched on February 11, 2013 aboard as at last V rocket from Vandenberg Air Force Base from California. So it provides high resolution satellite images with a 15-meter panchromatic band and 30-meter multispectral band for detailed land cover analysis, and is a free of charge. So you can purchase or you can download it from the USGS website freely. Then we have the satellite imagery. This satellite imagery of Guwahati. So the image is the image on the left that you can see is a false color composite image from Lancet 8, where different land features appears in distinct color. So the right image is a land use LULC, a land use and land cover map of Kamrup Metropolitan District that is craved out of this FCC Lancet image. So classifying areas, so the right image is a classified image into different categories such as agricultural land, built up area, dense forest, barren land, vegetation and water bodies. So this image on the left is a raw image, that is a satellite image, and on the right is a classified image that is done through machine learning. So Lancet 8 imagery plays a vital role in urban planning, environmental monitoring, resource management by providing detailed spatial data on land use changes over time. Moving on, we'll give an overview of Sentinel-2A satellite imagery and its application, particularly in agriculture and environmental monitoring. So, Sentinel-2A is a part of Copernicus Earth Observation Program by European Space Agency. It provides high-resolution satellite at 10 meters spatial resolution, which is crucial for detailed land monitoring. And the display in this image displays a false color composite highlighting vegetation in red. So the image shows various red colors. So this highlights vegetation, making it easier to analyze plant health, water bodies and even urban areas. Sentinel-2 data helps monitor crop health, assess yield, detect disease, and track weather patterns. So it supports in precise farming and land management by providing critical insights into soil moisture, vegetation stress, and overall land cover changes. So Sentinel-2A's high resolution spectral images enhances agricultural studies and environmental sustainability by providing accurate or up-to-date data for land use management. Then moving on to a more higher resolution, spatial resolution, this image represents the land use and land cover data and satellite image of Almora city, Uttarakhand. So on the left we have a high resolution satellite image captured using LIS 4 sensor from ISRO's NRSC with a 5.8 meter spatial resolution, which is more detailed than the previous two, that is the Sentinel and the Lancet. So the reddish area indicates vegetation due to the infrared spectrum, while the bluish white regions represents built up areas. Okay, so on the right there is a land use land cover map from 2013 that classifies the areas into 5 categories. So we can make a more detailed LULC map using a more detailed information, special satellite imagery. So this visualization effectively demonstrates how different spatial resolution affects in different land use and land cover mapping. Moving on, we have a more detailed information, that is satellite imagery of Almora city of Uttarakhand captured by the PLIDAS data from the European Space Agency with an impressive 0.5 spatial resolution. So on the left, the very high resolution image offered a detailed view of Almora's urban landscape, clearly showing individual buildings, roads, and natural features. Such detail that we can even see the colors of the rooftop. So, this high detail is crucial for urban planning, infrastructure monitoring, etc. On the other hand, we have LULC map of 2018 produced using this 0.5 spatial resolution satellite image. So comparing these maps with earlier data like the 2013 can reveal changes in urban expansion, deforestation or land degradation, aiding to better environmental and developmental planning. So this is all about the spatial resolution or the resolution of images and the image analysis part. So next we will study about the visual interpretation or an image, how image is interpreted. So moving on, visual interpretation or image interpretation in context of remote sensing. It is a process of analyzing images to identify objects and understand their significance. In remote sensing, this method is used to extract both qualitative, for example, types of land cover, and quantitative, for example, area measurement information from images. It involves identifying various objects on the terrain, which can be natural or artificial and may appear as point, lines, or polygons. So, a remote sensing interpreter follows a logical process to detect, measure, and evaluate features like environmental and cultural objects as well as their patterns and spatial relationships. So, in essence, image interpretation helps transform complex satellite or aerial data into meaningful insights for applications like urban planning, agriculture, and environmental monitoring. Moving on, the basic principle of image interpretation and the factors that influence how interpretable an image is. It, it depends on the nature of images. So, firstly, image captures from the air or space provide a visual interpretation of the Earth's surface, showcasing its landscape patterns. Secondly, the patterns in images. So, the patterns are composed of indicators related to the physical, biological, and cultural features present in the landscape. Thirdly, we have environmental consistency. Similar conditions in similar surroundings tend to produce similar patterns, while different conditions reflect different patterns. The role of the analyst. So, the quality and depth of information extracted from an image depends on the analyst's knowledge, skill, expertise, and experience and understanding of the image limitation. So, a successful interpretation combines visual clues from the image with the interpreter's expertise to accurately assess landscape features and their significance. Moving on to the uh, elements of image interpretation based on their orders and methods of search. Okay, firstly, we have the primary elements. These are the simplest and the first thing we notice, like the location, tone, and color. So these basic elements are essential for identifying features quickly. In secondary elements, which involves more detailed characteristics like size, shape, and texture. This detail builds on primary elements. Then we have the tertiary elements. These are more complex patterns such as shadow, height, depth, volume, and slope, which require careful observation. Then we have higher element. These elements rely heavily on context, including site, situation, and association. So they involve understanding how objects relate to their surroundings and the most advanced method of search. For deeper interpretation, analysts used collateral data, that is, additional information to support their findings. Then, collateral data, then we have convergence of evidence, combining multiple clues for accurate interpretation, and then thirdly, multi-concept approach. Okay, so integrating multi-concept approach is integrating different concepts to form a comprehensive understanding. In short, uh, interpretation starts with simple visual clues and progresses to complex analysis using both logical methods and supporting data. Okay, so first we will focus on the concept of shape in what the importance of shape in image analysis or visual interpretation. So shape refers to the general form, structure, or outline of object, which helps in identifying them. So the shape depends on the object's outline. Various shape types include linear, curvilinear, circular, elliptical, radial, square, rectangular, triangular, hexagonal, amorphous. Straight edge shapes are often seen in man-made urban areas or agricultural fields, while irregular shapes are common in natural features such as forest. Exception occurs when human activity alters the landscape, like roads or clear cuts. So additionally, uh, circular shapes often indicates farmlands or square shape. In square shape indicates farmland irrigated by rotating sprinklers systems. So these are some of the examples. In short, recognizing these shape patterns help analysts distinguish between natural and man-made features in images. So this image is an example of how different shapes are seen in aerial or satellite images, which are key in image interpretation. Firstly, we have the triangular shape. Triangular shapes are seen in objects like airplane, where the wings and the fuselage creates a distinct triangular outline. Then moving on to the rectangular shape, which is common in man-made structures such as buildings and storage units. Then we have the pentagon shape, a rare but recognizable geometric structure like the famous Pentagon building. Then we have the curvilinear shape found in winding roads, highways, or river system. So the curved outline distinguish natural or complex engineered structure. Also the curvilinear shape of rice fields. So the terraced fields designed with curved pattern to follow the natural landscape contours. Then lastly, we have the radial shape, typically seen in natural formations such as palm trees where elements spread outwards from a center point. So this example highlights how shape helps in identifying and differentiating different natural and artificial features in images. Then we have the concept of size in image interpretation. Size is a key factor that depends on the scale of the image. While analyzing imagery, it's crucial to assess both the absolute size of object and their relative size compared to the other feature. For instance, when identifying land use zone, large buildings like warehouses or factories often indicates commercial or industrial areas. Smaller buildings are more typical of residential areas. Understanding size helps distinguish different types of structure and their likely functions in a given landscape. This image illustrates examples of objects with identifiable sizes to help in image interpretation. Recognizing these common reference points allows us to better judge scale in aerial or satellite images. Automobiles are about 15 feet long and 6 feet wide, useful for identifying parking areas or streets. Then the railroads uh, provides a linear reference often seen in industrial or transport hubs. Trailers, typically 45 to 50 meters long, are common in shipping or warehouse zones. Then the baseball grounds with key distance like 90 feet for base path and 60 feet for pitcher's mount to home plate provide recognizable shapes in recreational areas. Then we have the air conditioning units are often comparable to size to cars in size and can be used to distinguish commercial or industrial buildings. By recognizing these standard images, we can understand better the scale and purpose of different features in aerial imagery. Now, the concept of pattern in image interpretation. Pattern refers to the recognizable arrangement of objects in a scene. When objects are consistently spaced or share similar textures and tones, they create a distinctive visual pattern. Example includes orchards with neatly spaced trees or urban streets with regularly placed houses. Identifying such patterns helps to quickly interpret the type and layout of land features from aerial or satellite images. Recognizing patterns is key to distinguishing different types of land use and structure. So this illustrates different types of patterns commonly observed in aerial imagery, each with distinct characteristics. First, we have the systematic triangular pattern. This organized layout forms a triangular grid often seen in structured arrangement like military aircrafts, parking, or large scale installation. Then we have the curvilinear pattern identified by winding curved paths. This pattern is typical in rural roads or natural development such as farmland routes. Then random or sinuous braided stream pattern. This chaotic pattern is commonly seen in natural river system where water channels splits and merge unpredictably. Then the systematic linear row of potatoes. This orderly pattern shows linear rows in agriculture reflecting organized planning methods. Then the radiating road patterns common in urban cities. This pattern features rows radiating outward from a center point such as a city square or a roundabout. So these patterns are key indicators for interpreting land use development and natural formation from aerial imagery. Next, the concept of tone in imagery. Tone refers to the relative brightness, hue, or color of objects in an image. It is crucial element for distinguishing different features or targets. Variation in tone helps identify shapes, textures, and patterns in images. The degree of darkness or brightness is determined by how much light a surface reflects within a specific wavelength. In similar terms, tone helps us visually differentiate objects in an image based on their lightness, darkness, or color. This illustrates how the tone and color are fundamental elements in image interpretation. So the three grayscale images represents individual spectral bands. Green band captures mid-visible spectral detail. Then the red band enhances contrast between different surface features. Near infrared band highlights healthy vegetation as highlight vegetation health, such as healthy vegetation appears bright. So the bottom image is a false color composite using RGB green, red, green, and blue. Then the image appears in red, a vegetation appears in red, while water bodies and other features are represented in different shades based on their spectral reflectance. These techniques help in distinguishing land cover types effectively, and also emphasizes how different spectral bands and their combination assist in better analyzing and interpreting satellite imagery. Then the concept of texture in imagery. Texture refers to the arrangement and frequency of tonal variation in specific areas of an image. It can be described as smooth or coarse. Rough textures appears molted, mottled with abrupt changes in abrupt changes in gray levels across small areas. This is common in irregular surfaces like forest canopies. Smooth textures show minimal tonal variation, often seen in uniform surfaces such as field, asphalt, or grassland. Texture is especially important for distinguishing features in radar imagery. In short, texture helps identify the surface characteristics of objects by examining their tonal pattern. This illustrates different types of textures using real life examples. So, on the top left, the avocado field shows a coarse texture while the grass and road areas have a smooth texture. Then the top middle, the pine areas have a coarse texture while the water lilies exhibit an intermediate texture. Then the top right, the pine logs display a distinct coarse texture with clear patterns. Bottom left, the cornfield represents a coarse texture with dense, irregular tonal variation. Bottom middle, the irrigation system appears with a mottled texture, indicating a mix of smooth and rough areas. And lastly, the bottom right, the Mississippi River region shows a variety of textures combining smooth water patterns with coarse vegetation. This example shows how texture difference can reveal surface characteristics in imagery. Then the role of shadows in image interpretation. Shadows can be useful because they provide clues about the profile and relative height of object, making identification easier. For example, tall structure cast longer shadow, giving us insight into their height and shape. On the downside, shadows can also obscure detail, making objects within them hard to detect or interpret. Despite this limitation, shadows are valuable in enhancing or identifying topography and landforms, especially in radar imagery where they highlight terrain variation effectively. So this image showcases how shadows enhance interpretation in imagery. In the first image, people and bench shows clearly shadows clearly define the presence and shape of individuals and objects, making them easier to identify. Then the second arc of glory, Vena, shows how shadows highlight architectural features and provide depth and giving insight into the structure's profile. Then the bridge sign shadow Demonstrate how shadow reveals otherwise less visible objects like overhead signs. Then in the Pyramid of Giza, the shadow emphasized the pyramid's triangular shape and height. The house image uses shadows to distinguish the building's structure and surroundings. Lastly, the shadow fall image shows how shadow outlines landforms and water bodies, helping identify terrain features. So overall, this example illustrates how shadow provide crucial clues about height, shape, and object visibility in image interpretation. Then we have site. The concept of site in image interpretation. Site refers to the topographic or geographic location of an area, which plays a crucial role in identifying vegetation types. Knowing the site helps in recognizing special environmental conditions that influence plant growth. For example, certain tree species are commonly found in well drained upland areas, while others thrive only in specific geographic regions. In short, understanding the site's characteristics can greatly aid in identifying vegetation and land features based on their natural location. This image shows an industrial facility, likely a power plant or a processing plant, viewed from above. Thus, the key feature includes large infrastructure elements such as cooling towers, storage tanks, and access roads. The presence of water channel suggests this facility might use water for cooling or as a part of its operation. So the layout reflects organized zones for machinery, storage and transportation. In aerial interpretation, this type of structure is often identified based on their distinct geometric patterns, large-scale infrastructure and proximity to water bodies for industrial purposes. So that's the importance of site in image interpretation. Then the concept of association in identifying feature based on their surroundings. Association considers the relationship between the recognizable objects or features that are commonly found together. For example, commercial properties are often located near major roads or highways, while residential areas are typically found near schools, playgrounds, and sports fields. Understanding this association helps in identifying land use patterns and specific location effectively. This image is an aerial view of what appears to be an industrial facility, possibly a power plant or a large construction site. Key features like large cooling towers, storage tanks, and complex infrastructure indicate that this site is involved in heavy industry or energy production. This connection to the concept of association where certain features are typically found together. For example, cooling towers are often associated with power plants, while large warehouses and store tanks are commonly associated common in industrial zones. Recognizing these patterns helps in identifying and understanding the land use from aerial or satellite imagery. Then the concept of resolution in image interpretation. So resolution, as I already explained in the previous slide, determines how clearly objects can be seen in an image, and it depends on various factors. If objects are too small or have low contrast with their surroundings, they may be difficult to identify. Additionally, factors like image color and the condition of the image can also influence the accuracy and success of image interpretation activities. In essence, higher resolution images provide more detail, making interpretation easier and more effective. This is an example of how spatial resolution affects image clarity and details using the image of Harbour Town in Hilton Head. Okay, so higher resolution like 0.5 meter provides 0.5 meter or 1 meter, provides clear or detailed visuals, while where objects like roads, buildings and trees easily distinguishable. Then as the spatial resolution increases, moving to 5 meter or 10 meter and beyond, the image becomes increasingly pixelated. Okay, that is, more pixels are seen, making it difficult to identify individual features. So the diagram on the bottom right illustrates the concept of ground projected in instantaneous field of view, showing how large pixel sizes cover broad ground areas, reducing the image detail. In essence, this highlights that higher resolution provides more detail and useful information, while lower resolution images lose images. So, while the lower resolution images lose clarity, limiting their practical use for detailed analysis. With that, I end my presentation today. Again, I'll come up with a new topic in tomorrow. Thank you.